Well, dear friends, let's see what is polarization and how to develop an idea. See, as a name itself indicated here, and it self-manifested. Polarization means something related to the positive and negative pole, basically. And here I have written polarization of ions because polarization of molecules is also a phenomena. But here I am not talking about the polarization of any molecule. So polarization of any ion, you can define this very simple words, that it is the relative displacement of relative displacement of nucleus relative displacement of nucleus and the electrons of the outermost electron shell, and the electrons of outermost outermost cell right. Relative displacement of nucleus and the electrons, right, of the outermost cell under the influence of influence of influence of electric field or field produced by I mean adjacent ion. See, this is the simple definition: relative displacement of nucleus and electrons of outermost shell under the influence of field produced by adjacent ion, right. Now see, I'm showing you one figure here. It is see, dear friends, this is a very good picture to explain the polarization. See, this is a cation and this is anion, and this is ideal ion pair without polarization. This is the ion pair without polarization. Without polarization. So if you see, the size of both is comparable. So when the size of ions is comparable, there is no polarization and bond is ionic. So ideal ion pair, you can say this. But see here, this is what I mean, with a dotted line, it is shown ideal. So this is cation, and this large size atom ion is anion, and dotted line is the actual. And you can see that the electron density of this idealized ion pair is shifted towards here, and this also have some deformed. So relative displacement of nucleus and what, obviously when electron cloud will shift one side, nucleus also with respect to electron cloud that will shift, and this is what the covalent character dominates. Now see, this is the original shape of and this is the this is what actual cation, and this is actual anion, and this is after polarization, this covalent character polarization, this is the electron cloud deformed like this. So basically polarization is deformation of symmetrical electron cloud of ions under the influence of electric field or field, and this field is definitely offered by the adjacent ion, right? So here a covalent character is dominated. In this case the covalent character dominated. So this is the polarization. These B and C represents the polarization. So hopefully all of you are clear in the idea of polarization. What is the meaning of polarization? Okay. So this is polarized ion. This is with the polarization, and these two ions are without polarization. Okay, so this is the polarization. One more term is we are using here, that is the polarizability. So polarizability is right? Polarizability of ions. So polarizability of ions is ability to deform, right? Polarizability is ability to deform under external field. And obviously this external field is offered by the what neighboring ion or adjacent ion. So here if you see, this larger ion shows the polarizability. Right? So this polarizability is characterized by the following features. This is very important point. So polarizability, it is characterized by the following features. Number one, when the identical magnitude of charge, means suppose that two ions have same charge. Suppose that two ions have same charge. Right? And equal and have equal size. Means what I am taking first condition, if charge magnitude of charge is same and same ionic radii, right? Then the polarizability, then in this situation, the polarizability of an ion is more than cation. So then means if same charge and equal size. If suppose that one cation and one anion, means if you have cation and anion both having same charge, means +1 and -1, and both have what equal size, then the polarizability of anion is more than the polarizability of what cation. Then polarizability of anion is more than cation. Don't confuse with that. Okay, if the size of anion and cation and charge is same, then they will not polarize each other. Okay, they will not polarize to each other, it's okay. But suppose that cation is separately kept with some other external field and anion is kept in some other electric field, then which one have more ability to get polarized and which has less ability? So in this situation, when you take this cation and anion with have same charge and have same size and you are kept together, then there is no one is polarized to each other. But here I am comparing the relative polarizability under the different situations. So this is the first condition. Now come to the second condition. Second condition, the if the electronic configuration is same, if electronic configuration is same, suppose that you have two or different ions have same electronic configuration, then the polarizability is then polarizability is directly proportional to radius of the ion. Means if electronic configuration is same, then with the increase in the size or electron layer, you can say the polarizability is increases. Suppose that if you have F minus, see, electronic configuration is very important feature. Cl minus, Br minus and I minus all have same electronic configuration. So this is the order of polarizability. Order of polarizability. Similarly, if you take Li plus Na plus K plus Rb plus Cs plus, so this is also the order of polarizability. So I think second point is clear to all of you, that how this polarizability is changing if electronic configuration is same, then polarizability is directly proportional to the radius of what ion. Clear? Okay. This is the second point. Third point, this is also a very important point. Third point, if if charge and radius is same, and radius is same for two ions, two ions, then the polarizability, then polarizability of ion, polarizability of ion with 18 electron shell, with 18 electron shell. For example, if you take what mm, copper plus CD2 plus, right, is higher than higher than that of ions with noble gas configuration, higher than that ions with 8 electron shell or noble gas. This example is Na plus and Ca2 plus, right? Na plus and Ca2 plus. See, if you see the electronic configuration of Cu plus, so you will find 2, 8, 18. And if you see the configuration of Na plus, then you have 2 and 8. Both have almost same size. So this is the order of polarizability. Order of polarizability. Right? Clear? Similarly, so these 3 points will cover all the cases of your, see, this is called pseudo noble gas configuration. Sometime you may find this. This is called pseudo noble gas configuration. Pseudo noble gas. And this is called noble gas. Noble gas configuration. Right? So basically, the polarizability is governed by all these 3 points, and all the examples can be covered. Similarly, the polarizing power, it is the ability to deform the other ion, right? So polarizing power. So let's talk about some about the polarizing power. So polarizing power, it is defined as the ability to deform or polarize another ion. Polarizing power is the ability to deform the other ion, right? And you know, it increases with increasing charge. Polarizing power, it is is directly proportional to, polarizing power is directly proportional to the magnitude of charge, and it is inversely proportional to the size, radius of right, radius of eye, and mainly it depends on the what electronic configuration. So how electronic configuration, and see, polarizing power basically we observe for cations, right? Basically we see this polarizing power, I mean with for cations, not for it is not much useful for anions. So polarizing power is mainly we observe for cations, right? So polarizing power, it is electronic configuration. So main see, this is first feature, and second feature is electronic configuration. See, ions with noble gas electronic configuration, we can write ions with noble gas configuration, means 8 electron shell, 8 electron shell, 8 electron shell have the less polarizing power, has less polarizing power, than uh, unfilled electron layer. Unfilled electron layer. For example, Ti2 plus, Fe2 plus, lead2 plus, etc. Many examples you can. And if charge is same, radius is same, and then polarizing power uh, is directly proportional to pseudo noble gas configuration. Means 18 valence shell, 18 electron shell. This is very important point and very effective feature. For example, if you can see Cu plus, Ag plus, Zn2 plus, Cd2 plus, Hg2 plus, and you will find that mostly compounds of these ions are covalent in nature, have more covalent character than ionic character, right? So these are the points uh, which affects the polarization and polarizing power of ions. See some examples for this and some property. See one question that see the radius of Na plus is equal to the radius of copper plus. Both have same size, right? And both have same charge, means same size and same charge. Same charge. Now if you see the chlorides of both, means NaCl and CuCl. So now tell me, chloride chloride is common in both, so leave that. You have to decide on the basis of this. So for cation, what you are going to see, polarizing power or polarizability? Obviously polarizing power. So which has the more polarizing power? So if you find, then you will find that Cu plus has more polarizing power than Na plus. Polarizing power. Why? Because this is 2, 8, 18 and this is 2, 8. Now see, if it has pseudo-noble gas configuration in 18 electron shell, so this has more polarizing power if other things are same. See here, if charge is same, radius is same, then this is very effective feature, very effective feature which affects the polarizing power, right? So if ions with noble gas configuration 8 electron shell has the less polarizing power than the unfilled electron. So means if it has 8 electrons in the valence shell, then it has less polarizing power. So this is the reason why this melting point of sodium chloride is 801 degrees Celsius, but of copper chloride is only 430 degrees Celsius. This is the melting point. So the melting point of sodium chloride is more than copper chloride. Why? Because you can say that CuCl has more covalent character, has more covalent character, due to polarization. Now see that the two ions not necessarily form always ionic bond, and one rule is there also, that that is known as Fajan's rule. So if other things, if all other things are same, then a smaller cation has greater tendency to form a covalent bond covalent bond with larger anion, with larger anion. Now see, means a cation and anion cannot form always ionic bond. Hence proved that this you can say cation and anion may form the covalent bond. Suppose that if you compare the covalent character between suppose that LiCl is given, LiBr is given, Li is given. So if covalent character, we will talk about covalent character. So Li is what? Come, leave that. Now Cl minus, Br minus, I minus. So which has the largest size? I minus has the largest size. Cation is common. So polarizability of I minus is maximum. So it has maximum covalent character. So higher the polarizability, higher the polarizing power, higher the covalent character. So this is the order of covalent character. Order of covalent character. So polarizability and polarization induces the covalent character in a ionic bond, right? And or you can say in ions. So it is not necessary that ions always form what? Ionic bond. Ions may form covalent bond if they have sufficient space to get polarized, or if they fulfill the condition of polarization, right? So this is all about what? Polarization and induction of covalent bond in ions or ionic compounds, right? And consequence of that, this properties of molecule like melting point, if we increase this covalent character, then melting point will decrease, right? Okay, good. Well, see, this is the order of what? Covalent character. So if the covalent character is maximum here in lithium iodide, so in the same manner as in the previous case, I have shown you here, see the melting point. So you can arrange them in the order of melting point as well. So you can say that the lithium chloride has the highest melting point, then lithium bromide, and then lithium iodide. So this is the order of melting point. Melting point. So in this way you can use this Fajan's rule. Although they see this Fajan's rule, one thing I would like to say here, this Fajan's rule, Fajan has not given any quantitative parameter or experimental parameter to measure the covalent character in the molecules. This is the reason why this rule is not included in the regular circular of what? IUPAC. But qualitatively you can use this rule, and it is popular, right? Similarly, if you see other cases, suppose that if you take NABr and MgBr2 and AlBr3, So don't see the number of bromine atom, how many bromine atoms are there. Don't see that. Bromine is common. So you have to decide on the basis of size of Na plus. See, Na plus, here Mg2 plus, and here Al3 plus. So which property you are going to see here? Polarizability or polarizing power? So definitely you will go for polarizing power. Polarizing power. Why? Because usually in such type of binary cases where cations and anions both are present, so we always see uh, for cations polarizing power and for anions polarizability. This is the, I mean, majority of cases you have to consider this. So polarizing power is maximum for this. Why? Why this order? Why this order? Because the size of Al3 plus size is smallest and magnitude of charge is maximum. So because size of this Al3 plus, what is the order of size? So order of size is this Na plus, Mg2 plus, Al3 plus. So the order of size is this. Order of size. See, order of size is this. Magnitude of charge, positive charge is maximum. So polarizing power is maximum for this. And if polarizing power is maximum, then this has the maximum covalent character. So this is the covalent character order, right? Covalent character order. And now if you have covalent character order, now you can arrange them in the melting point also. So what is the melting point order? See how all these properties are related with I mean each other, NABR. And if you are going to learn every order, then it is very difficult for anybody who I mean who can learn this. So this is the order of what? Melting point. Order of melting point, right? So in this way you can explain the I mean application of this Fajan's rule. One more I mean interesting case we have, that see, this is very important. If you take the halides of silver, AgF, AgCl, AgBr and AgI. Suppose that this is the case. Now cation is common, so leave that. Compare the anions. Here you have F minus, here you have Cl minus, Br minus and I minus. Now what here you are going to check for anions, because this is the point of difference. Cations are same, so you have to check here polarizability. Polarizability. So if you remember, then you have given the idea that if electronic configuration is same, then with increase in the size, polarizability increases. So this is the polarizability order. Polarizability order. And this is the size, order of size also. F minus, Cl minus. So why I should write here? Polarizability order, polarizability and size order. So all of you are knowing that if the greater the polarizability, greater the covalent character with the same cation. So what is the covalent character order here? So the covalent character order is this. Order of covalent character. Order of covalent character. Right? So what is the melting point order? So the melting point order is AgF, AgCl, AgBr and AgI. This is the order of what? Melting point. Melting point. Right? One more property here we can consider, that is what? Solubility. So all of you are knowing that the covalent compounds, if you have more covalent character in the compound, then it is less soluble in water, and this also here explained. But I'm not suggesting you that every time you should correlate this solubility with the covalent character, because here it is okay, but not always true. So here I am explaining by using this, but this is not the general rule, that if a covalent character dominates between two ions, then it is always less soluble. So solubility you can relate in more than 90% cases. You may get a more than 95, even you get the correct answer, but not always. Some exceptions are there. So but here it is okay. So solubility also we can correlate. So AgF is this most soluble, then AgCl, then AgBr, then AgI. This is the order of solubility. Order of solubility in water. In water. Right? You can correlate, but there are few exceptions, and that I will discuss obviously in the same topic, ionic compounds. Okay, and if you can see here that they are practically insoluble in water. These salts are practically insoluble. So this is order of solubility. Order of solubility means relative order is solubility. You cannot say that okay, all are soluble in water. Relative means if maximum, if under identical condition you take same quantity of every salt in the given amount of water, then AgF maximum will dissolve. So I am now I am telling you the practicality. What is practicality? That this is soluble in water, soluble, absolute sense, soluble in water, and they are insoluble, practically insoluble. Practically insoluble. Right? So these are practically insoluble in water. Okay, and you know this AgBr, AgCl, white precipitate of this AgCl, this is soluble in ammonia. Soluble in ammonia. AgBr also soluble in ammonia. Also soluble, but less than AgCl. Also soluble in ammonia, but less than AgCl. And AgI, it is insoluble even in ammonia. In ammonia. So you can say AgI is the least soluble. How they are, these two are soluble? This is due to the complex formation. Complex formation with ammonia. Complex formation with ammonia. So they will provide the threshold quantity of Ag plus ion which can form the complex with ammonia, because AgCl as a whole cannot form the complex with ammonia, Ag plus. So they are in ammonia, aqueous ammonia, what they will provide a critical amount of silver ion which can initiate the reaction with ammonia, but AgI cannot provide that critical amount of silver ions so that it can show the solubility in ammonia. So these are very important points. In different chapters you will have this property, like in organic chemistry. You may have, I mean, suppose that you have alkyl halide and you are treating that alkyl halide with silver nitrate. Silver nitrate is a fairly soluble salt, and in fact all nitrates are soluble. So if you take Ag silver nitrate with some alkyl halide or alkyl chloride, and see that Ag plus will form AgCl, and with reacts with chlorine of alkyl chloride and form AgCl precipitate, and it promotes the formation of carbocation. So all these properties, chemical behaviors, these are the fundamental properties of these I mean molecules, and they are useful in expressing the other properties in other chapters as well. That's why it is here discussed. So at least what examples I am taking here in the lecture, at least those examples you have to prepare. Every time you have to prepare, right? And if you prepare more than that, then it is always welcome, right? One more thing, suppose that if it is given BeCO3, MgCO3, CaCO3, SrCO3, and BaCO3. So all these carbonates are thermally unstable. They decompose at different temperatures, right? But if you I mean move down the group, thermal stability increases. So on the basis of what we can explain here, see Be2 plus Mg2 plus, because the point of difference is this: carbonate, carbonate, carbonate is same in all, leave that. Mg2 plus Ca2 plus Sr2 plus and Ba2 plus. So this is the order of size. Magnitude of charge is same. Order of size. Now what you can assess for this? Polarizing power. Polarizing power, right? So which has the highest polarizing power? This has the highest polarizing power. And if this has the highest polarizing power, then this has the maximum covalent character. Then this has the maximum covalent character. So the order of covalent character among these carbonates is this. Order of covalent character. So maximum covalent character you will find here in BeCO3 region. I have already explained that on the basis of polarizing power, this has the maximum polarizing power. So if you want, you can rearrange that Be2 plus Mg2 plus Ca2 plus Ca2 plus Sr2 plus and Ba2 plus. This is the order of polarizing power. polarizing power, right? So this is the covalent character. So thermal stability, you can correlate with the covalent character. So the thermal stability order BeCO3 least stable, then MgCO3 is more stable than this, CaCO3 is more stable than SrCO3 and BaCO3. So this is the thermal stability. Thermal stability, right? Order of thermal stability. So with the help of covalent character and ionic character, you can explain this thermal stability of different carbonates as well. And in the first group, lithium carbonate decompose like all these carbonates decomposed, Li2O plus CO2, and all other carbonates are stable. Carbonates are stable. So sodium carbonate, potassium carbonate, and cesium, rubidium, all they are thermally stable, right? Thermally stable. So what conclusion we can say? We can say that in the carbonates of first group, the ionic character is sufficient, covalent character is less, that's why they are stable. But here this lithium, all of you are knowing that it is showing the diagonal relationship with the magnesium 2 plus, so it is covalent. So the maximum covalent character in the lithium carbonate in the first group, what carbonates. So these are the some application of this covalent character versus ionic character in between two ions, and with the difference in the size of anion and cation, this will depends, right? So in the next lecture I will discuss lattice energy, that I have already promised you that lattice energy and solubility I have to discuss in the detail. Okay.